we discussed the first approach for deriving the running time for the MergeSort algorithm, which is to analyze its recursion tree visually. And let's now move on to the second approach, which is also important to learn. And the second approach will be similar to how we did it for the binary search algorithm, which is we have to analyze the Java code of the implementation, and then to really derive the recurrence relation from there, which we're going to do, and then to solve it by unfolding. That's what we're going to do. Right, so let's now try to fill in the answer for the recurrence relation. We got two base cases when the list is empty and when the list contains only one element. So these two base cases nicely correspond to the Java code. And also, we got the recursive case as well. Let's talk about it. Let's start with a simple one. You can see here, this is the base case number 1. When the size is equal to 0, in that case, what do? We simply do some simple variable assignments and creating the objects. So that'll be just 1, just constant. And what about the second case? The second case, let me use a different color here. It's going to be else if the size is actually equal to 1. In that case, we're still going to do some simple assignments and also try to add an element to the end of the array list, which we can assume is actually a constant amount of time, which is efficient. Right? So that will be 1 over here. What about the recursive case? For the recursive case, let me just box them over here, and it will be somehow corresponding to how we discussed about the visual recursion tree. Let's now talk about each one of them. This one here is just about to calculate the middle point for splitting. And these two over here are just about the splitting themselves. So these three are simply just constant amount of time. So all these three will be simply big O of 1. All these three. And let's go further. You can see the left over here and also the right over here. What are their sizes? Right? You can think about you're really trying to sort. So the left and also you try to sort the right. And we know very well, based on the calculation for the middle, their size over here, the size is actually equal to n over 2, as we actually could see for the recursion tree diagram over here. So that means we should really do, how many times are we doing the recursion? We have to do the recursive call on the left and on the right. Each one of them is going to be like this. Each one of them, let me use pink, is going to be given a list of size 2. We have to do t over n over 2, that's for the left, plus t of n over 2, that's for the right, and plus we have seen these initial 3 steps are simply just big O of 1. But what about the last step, which we haven't seen yet? This one over here is about the merge, and we learned before the merge itself is actually going to be big O of n at every level, right? Or it can be the summation of the sizes of the left and right list, which in the worst case would be n over 2 plus n over 2, which will be big O of n. Right, so over here we should really say plus n over here. You can think about when you try to collapse this one here and this one over here, of course this one here is going to dominate. So the overall answer, and of course you can simplify this if you want to. And this part over here can be simplified into, of course, 2 times. This one over here will be just 2 times t of n over 2. Right? We do it once for left and do another time for the right. So the overall answer will be t of n is equal to 2 times t of n over 2 plus n. And we also got the 2 base cases over here. So that's a recurrence relation, right? There should be no surprise to you, but you should really understand exactly how we derive them. Let's now move on solving this recurrence relation for the MergeSort algorithm. And then the way we're going to do it is by unfolding the equation, and hopefully we can know the pattern and see how it would look like when we reach the base cases. Let's now start doing it. So I will start with t of n. According to definition, it is equal to 2 times t of n over 2 plus n. Let's write it down. So t of n, by definition, is 2 times t of n over 2 plus n. And let's do the first unfolding. Let's say I want to unfold this expression over here, meaning that we're going to substitute n over here by n over 2. And that means every occurrence of n over here is going to be replaced by n over 2. And you can see n over 2 over 2 is going to be n over 4. Right? That's the substitution process. Let's write it down for the result. It's going to be equal to 2 times, and then I'm going to leave some space over here, and then plus n. And for this part here, it's going to be t of 2 times t of n over 4, as we explained, plus n over 2. Right? It's very important for you to see that. And let's do some simplification right away. I kind of know the solution, so that's why I can suggest maybe some intermediate analysis that we can do right away. Can we just try to simplify this a bit to see what it should be? Right? Let's try that. And we're going to say 2 times 2 over here. So we're going to say 2 times this one here plus this one here. Apparently 2 times n over 2 is going to be n. Right? Let's now just do it. This one over here is going to be 4 times t of n over 4 plus 2 times n over 2 is going to be n plus n, 2n. 2n. Right? You can double check about the result and convince yourself that's really the case. It will be very valuable to see this intermediate pattern as we go. Let's now move on to the next one. And for the next one, what we want to do is we want to, let's say, unfold this expression over here. And we'll do a similar substitution. We're going to substitute n over here by n over 4, as we said over here. So n over 4 divided by 2, n over 8. And also n over 4 over here, just replace it. Right? That's what we're going to get. Let's now write it down. So we're going to get is equal to 2 times over here, and this time is going to be bigger, I think, and then plus n. And we got an intermediate one, 2 times over here, and then plus n over 2. Right? That's what we had before. And now for the new one, this one over here, and let's make just a little bit more space for that. I think that'll be good. Right? So this one, how do we unfold? It's going to be 2 times t of n over 8 plus n over 4, as we sketched. And let's try to do some similar simplification if we can simplify it into something similar to this. Let's see if it is possible. Let's try. 2 times 2 times 2, 8 times t of n over 8. That one we can do first. Okay, so let's now write it down first. It's going to be 8 times t of n over 8 and plus something. Let's see what that something is. And let me use some other color to help us focus. So here we got 2 times n over 2. For that one we got just n. Right? And also, let me use another color. How about orange? We got 2 times 2 and then times n over 4. For that one, we also got n. And that's it. Right? So that means we got n plus n plus n. 3n. Right? That's kind of intermediate calculation you would like to work out by yourself. Right? So that'll be 3n over here. Right? For that, I'm just going to wipe out these two. But I'll still leave the trace over here in case you want to refer to them. And I can already see a pattern there. Maybe you can see that pattern as well. What we want to do is we want to say we're going to keep unfolding this until we can reach the base case. There are 2 possible ways for you to actually reach the base case. Either, let me refer to you, you can just go back to the slides and you will see the proof the unfolding I actually laid out over there. So this part over here is really about without the intermediate simplification, which I did. You can see I tried to do some intermediate simplification in the purple over here. I didn't really do these in the intermediate one to see what the simplification can be. I simply tried to do the unfolding as we did, and then I tried to figure out the pattern at the last step over here. This one also works, but that one requires a little bit trickier observation, which you have to make, but it's still valid. You can definitely refer to the slide as that's one way of figuring out the unfolding. Approach number 1. But I found that approach number 2 might be easier for you to actually work out the solution. Approach number 2 is, once we get each one of them, we're going to find out the corresponding simplified formats. So we will know that when we get to the final one, we can also simplify it in the similar format. So we're just going to work out this format only, which is much simpler than working out exactly this. Okay, so that's my rationale for you. You can choose which one you like. Either one works. Let's now choose this one here. But what exactly is really the pattern for this simplified form? Let's take a look. You should really focus more on the denominator over here. How about I use red? You can see the 4 over here is really 2 to the power of 2. And the 8 over here is 2 to the power of 3. Right? And the pattern really is the multiplicative constant for the t function is really the value of the denominator. When you can see when it is 2 to the power 2, it's actually equal to 4. When it is 2 to the power 3, it's actually equal to 8. Pattern number 1. Pattern number 2, the multiplicative constant for the plus n over here is corresponding to the exponent over here, 2 and also 3. Right? Let me highlight quickly about these two patterns. So you can see 2 to the power of 2, 4. 2 to the power of 3, and 8. Okay? Let's now highlight only just exponents. The 2 over here and the 2 over here. The 3 over here and the 3 over here. Right? So far clear. Let's now use this simplified pattern over here, simplified form, and we have observed its pattern already. Let's see what should be the simplification be when we reach the base case. We want to reach t of 1, basically. And let me remind you about 1. Well, the log property that we also went over when we talk about the derivation of the binary search running time. And if you recall, when we say 1 over here, we want to have the input size 1 is equal to n divided by n, and we really want to get into the form like 2 to the power of something. We want to say it will be n over 2 to the power of something. What should this be? And that's the log property that we spoke about earlier in the same lecture, right? For that one, I'll refer you to the earlier part of the lecture without repeating it, right? So this one here should be simply just log n with base 2, right? So that's really the intermediate value. You should really know how we can derive this one over here. And of course, if you really want to check with some value, you can try this. Let's say n is equal to maybe 8. In that case, 2 to the power of log 8 is equal to log 8 with base 2 is 3. 2 to the power 3 will get you back to 8. Right? Some quick check for you if you need it. All right, let's now move on to the final line over here. What we really want to know is when this input value over here is actually equal to 1. In that case, it's going to be 2 to the power of log n. Right? Let me do that. So what we want to have is, finally, we want to have, let's say, I think blue is okay. We want to have t of 1 over here. And we know that this one here can be rewritten as n over 2 to the log n. And according to the pattern of the simplified form, the multiplicative constant over here should be exactly equal to this denominator. And also the plus n over here, the multiplicative constant should be corresponding to the log n. Right? That's the two patterns we spoke about. The first one is going to be 2 to the power of log n. Okay? Multiply by that. And then plus the log n over here, the exponents, log n times n. Right? What's really this part over here? 2 to the power of log n will be n. This part here should not be too surprising. So this part over here is simply just n. Okay? And we know that t of 1, by definition, also we know that it's actually 1. Right? Let's now try to do a final simplification, and then we should be done soon. So what we get ultimately will be n times 1 plus n log n, which would be n times 1 plus n log n. That's what we have. And of course, this is going to dominate asymptotically. So we can drop the lower term over here. And which is equal to big O of n log n. This will be the final answer for the running time of the merge sort, which corresponds to what we actually derived from approach number 1 when we analyzed the recursion tree of the merge sort algorithm. Alrighty, so that's about the derivation. Again, there are two different approaches for you to unfold the recurrence relation. Either you can show the work about how the simplified form should really look like and observe the pattern of the simplified form rather than observing the pattern of the original, like a times 2 and also plus n, or actually not even plus n plus n over 2 plus n over 4. That would be trickier to actually observe. But if you want to do that, you can definitely compare your own answer with this one over here. You should know both. That's what I can advise. Alrighty, so now we're done with the complete discussion about the merge sort. And let's now move on to the next one, which will be quick sort.